Hi everyone. Last episode, we justified our choice of linear algebra for the framework of quantum mechanics, and we posited the following. Particles are represented by vectors in a vector space, somehow being superpositions of all possible outcomes of a measurement. Physical quantities, like energy, position, etc., are represented by linear operators on that space. In this episode, we are going to mathematically formalize the first of these ideas, how particles are represented by vectors. Since we are going to be using a linear algebraic framework, we should make sure we have a solid understanding of what a vector space is. Now, when I first learned linear algebra, I learned it in the context of arrows and columns of numbers, and I think most people first learn it this way as well. But a vector space is actually something much more general and abstract. To see this, let's look at the mathematical definition of a vector space. Formally, a vector space is a set of objects called vectors that satisfy the following rules. This might look overwhelming, but most of these rules just codify ideas that we already find intuitive. For example, this first one says that adding two vectors gives us another vector. The next one states that multiplying a vector by a scalar also gives us another vector. And a lot of the other ones just enforce intuitive notions about how vectors are added together and multiplied by scalars. See how these rules just enforce what we already expect from vectors? So, what is the benefit of defining a vector space like this? Well, this definition makes no mention of lists of numbers or arrows. Any set of objects that satisfies these rules forms a vector space. With the right rules, it could be fruits, it could be functions, or our familiar columns and arrows. Hopefully you're beginning to understand that linear algebra and vector spaces are all about structure and patterns, not about the type of object you're using. And it just so happens that the particular structure of a vector space is exactly what we need to describe the quantum world. So, now that we understand what a vector space is, let's apply it to quantum mechanics. Like we mentioned last episode, we want our particle to be represented by a vector in a vector space. More specifically, a vector in this vector space represents a quantum state. A quantum state is a mathematical object that holds all the physical properties of our particle. From it, we should be able to extract the possible positions, momenta, energies, etc. at any particular moment in time, as well as all the associated probabilities. Now, instead of using our typical vector symbol here, physicists like to use a different symbol for vectors in quantum mechanics. We will represent a vector using this notation here. When we write a vector in this way, we will call it a ket. This is still a vector, it's just a different notation. The reason for choosing this notation might seem strange, but its power will become apparent in later episodes. Now let's relate this notation to quantum mechanics. Remember from last episode, we wanted to represent our particle as a linear combination of all possible outcomes of a measurement, for example, energy. Therefore, we would have a list of quantum state kets representing each possible energy outcome, and our present quantum state is represented by a linear combination, often called a superposition, of all these quantum states, where the coefficient has something to do with the probability of that outcome. If instead we wanted to measure angular momentum, we would have a list of quantum state kets representing each possible angular momentum outcome, and we would have a different linear combination, but still the same present quantum state, and so on and so forth for each measurement we can make. In a later episode, we'll discuss how we get these lists of outcome states and associated probabilities. Now, here we have a finite list of outcome states, but it may very well be that we have infinitely many outcomes. I mean, think about it. What's stopping you from giving a particle more and more energy? We need to have outcome states for arbitrarily high energies. Therefore, we may sometimes have linear combinations of infinitely many kets, representing a superposition of infinitely many outcomes. In the next episode, we'll quickly discuss how this infinity brings some issues with it, and why a Hilbert space fixes it. But for now, let's assume an infinite linear combination doesn't cause any problems. But we do have a separate issue to address. So far we've been looking at the case when things like energy and angular momentum have a discrete set of possible values. But physical quantities are not always discrete. For example, let's look at position. So far, we do not have experimental evidence showing that position is discrete. An electron can be anywhere it pleases. There is no list of possible positions. In other words, position is continuous, not discrete. We want to be able to mathematically describe this within our theory. So here's a puzzle. Say our electron can have any possible position, although some may be more likely than others. How do we represent the quantum state of our electron using the kets of possible positions? Our typical sum won't cut it, since to have a sum, we need a discrete list of things to add together, and it's impossible to cover all positions using a discrete list, even if that list is infinite. So what we need is some mathematical operation that has the power to sum over a continuous set. See if you can think of one. You might have realized that the integral is an operation that does exactly this. I mean, think about it. To find the area under a function, the integral adds together the contribution from each tiny slice at every point along the continuous set of function values. The integral is exactly the continuous sum we need. So, let's use the power of the integral to write a linear combination when we have a continuous set of outcome possibilities. First, we want to write this as a sum, so we write the integral symbol indicating a sum. Note that the limits of integration are implicitly plus and minus infinity. Next, we are summing over all possible position outcomes, represented by variable x, so we need to have a differential dx to indicate that. Don't worry about where we put the dx. In many theoretical physics texts, you'll see it in front. Next, we need our kets, which we will label by the position they represent x. Lastly, we need our coefficients. We have a coefficient for every possible position x, meaning we need a number for each value of x. This is exactly what a function does, so let's use a function for our coefficients. And there it is. We have written a quantum state where the superposition is over a continuous set of outcomes. This can be very confusing if you're seeing it for the first time. Just remember that an integral represents a continuous sum. So this is just a continuous linear combination of outcome kets. Comparing this to our typical linear combination, hopefully you see that one is just a continuous version of the other. Before moving on, I want to spend a second discussing the coefficient function that we have here. It may seem weird to use a function in place of a coefficient, so let's see how it comes about. Let's pretend that position were indeed discrete. In that case, we would have a list of possible position outcomes and their associated coefficients. Let's plot these coefficients as a function of their corresponding position. So, for each discrete position x, we plot its coefficient c as a point. Now let's begin undiscretizing position. Let's close the gap between the possible positions, adding coefficients for all the positions that we're missing. As this occurs, the coefficients start getting closer and closer, and you see that they begin forming a line. In other words, they begin forming a function. For now, we just assumed this function must be continuous, but we'll justify this assumption in a later episode. See how we get the transition from discrete coefficients to function? Now let's note something important. Remember that in the linear combination of possible outcomes, the coefficients are somehow related to the probability of getting that particular outcome. Meaning, this function here somehow tells us about the probability of a particular position. If you have some previous quantum knowledge, maybe you know of another function that is related to the probability of position. Your mind might have jumped to the position wave function. And in fact, this function here literally is the wave function. We'll prove this in a later episode, but take my word for it. So hopefully you see that in the linear algebra framework, the position wave function is just the list of coefficients in front of each possible position ket. When I was first learning quantum mechanics, I always wondered how functions connected with the linear algebra framework, and hopefully now you see how. Many people often state that the wave function is a vector. Although functions can live within their own vector space, and you can frame quantum mechanics in that way, now you know what wave functions actually represent. Wave functions in quantum mechanics represent coefficients to kets whenever the list of kets is continuous. Now, what do these coefficients have to do with waves? For that, you have to wait until we derive the Schrödinger equation, so be patient. This is a lot to take in, so feel free to go back and really soak in everything we discussed. So, to summarize, in this model, a particle is represented by a vector in a vector space, also called a quantum state. We chose a special notation for this vector that we call a ket. This ket holds all the information about the particle. For any physical quantity, our quantum state is in a linear combination, i.e. superposition, of all possible outcome kets, with the coefficients telling us something about the probability of that outcome. Sometimes a physical quantity has a continuous set of outcomes, in which case we replace sums with integrals and coefficients with functions that we call wave functions. Next episode, we will dig deeper into the problems that an infinite vector space can cause, and we'll derive the need for a special type of vector space, one that we call a Hilbert space. Thanks for watching this episode.